This is University of Arkansas Physics and Human Affairs, Lecture 15, Fusion and Fission, for April 16th, 2020. Let's begin now, as we usually do, with poetry. Say it with me. An atomic nucleus is made of nucleons, which are protons and neutrons, and we all feel like dorks knowing nucleons are made of quarks. When a nucleus gets too big or a quark changes flavor, radioactive decay gives us all the energy we can savor. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Let's talk about two kinds of nuclear reactions that give a lot of energy, both in terms of power plants and also explosions. What we see here is the fission of uranium. So this is a uranium-235 nucleus. If you shoot a neutron at it, it'll capture that neutron and become uranium-236. Well, uranium-236 is extremely unstable. It immediately breaks apart, releasing a whole lot of energy, both in gamma rays and in neutrons and in thermal energy. That is, the two smaller nuclei are moving fast. They're hot. And if this is just a standard uranium rock, why, this happens randomly once in a while, takes a long time, the rock gets warm. Okay, but if you stuff a whole bunch of these uranium nuclei together in a really densely, tightly packed way, then each of these neutrons will hit another uranium nucleus and cause this to happen again and again and again and again. That's what we call a chain reaction, a nuclear explosion. Elements on the periodic table are made generally by nuclear fusion. And where they're made depends on what element they are. The universe began, remember, with an explosion of space-time and energy we call the Big Bang. In the first few minutes of the universe, the whole universe was as hot and dense as the core of a star. It was hot enough and dense enough for nuclear fusion. So in the first fraction of a second after the Big Bang, hydrogen was manufactured. The first few minutes after that, about 25% of all the hydrogen in the universe fused together to form helium. So hydrogen and helium were made at the Big Bang, with trace amounts of other light elements like lithium and beryllium. Even today, the cores of stars turn hydrogen into helium. That's what our sun's doing. When the sun gets older, it will manufacture heavier elements like carbon and a bit of oxygen, but that's it. A high-mass star can build heavier and heavier elements because its core is hotter and denser. The heavier the element, the hotter and denser the environment has to be for the element to be manufactured. So the most massive stars, at the end of their lives, will make heavier and heavier elements up to iron. Iron kills the star, for reasons we'll discuss later in this lecture. So once iron is manufactured inside a high-mass star, a red supergiant star, the star explodes, and that's what we call a type 2 supernova. Well, even more heavy elements are manufactured, ranging from magnesium up through zirconium. When our sun dies, its core will be left behind as a white dwarf, a dense ball of carbon and oxygen, and a white dwarf if it is in a close binary orbit. That is, if you have a white dwarf co-orbiting with another star, that white dwarf can steal hydrogen from that star and get more and more massive until it gets too massive. The white dwarf gets squeezed by gravity so tightly because it's so massive it explodes. That's what we call a white dwarf supernova, or a type 1a supernova. That too manufactures elements through nuclear fusion. Elements from number 14 to number 30, silicon through zinc. When a high mass star explodes, it doesn't leave its core behind as a white dwarf, like our sun will be. A high mass star leaves behind its core as a neutron star, a dense ball of neutrons, essentially a giant atomic nucleus, an atomic nucleus the size of a city with the mass of a star. And occasionally, very occasionally, you'll get two neutron stars in a binary orbit. And sometimes they will spiral together and explode. We call that a kilonova. And the kilonova, the merging neutron stars, are what make the really heavy elements. The elements on the periodic table that we think of as being valuable because they're rare, because they're hard to manufacture, things like gold and silver and platinum. These are rare elements on Earth because unlike iron, which is made from exploding red supergiant stars, that happens all the time. Iron is easy to manufacture in space. There's lots of iron out there. The gold is manufactured when neutron stars merge. That's a pretty rare event. So gold, silver, platinum, the rare metals, the heavy metals, the valuable metals. These are ones that were manufactured by a rare event in space, the merging of two neutron stars. Now that was a whole lot of information, so let's zoom out. What we're really saying is the Big Bang made hydrogen and helium. Everything else is made by stars. And they're made from nuclear fusion, with the exception of hydrogen. Hydrogen is just a proton. That's all hydrogen is. It's made by quarks combining, and this happened in the first thousandth of a second after the Big Bang. The heavier elements are all made by fusion. Essentially, they all started as hydrogen, and then nuclei built up to form heavier and heavier elements. Sometimes small nuclei fuse together to form unstable elements that then break apart again to form lighter elements again. But nonetheless, the net result is over time, more and more heavy elements have been manufactured in the universe. So let's revisit the difference between fission and fusion. Fission is the breaking apart of nuclei into smaller ones. Fusion is the joining together of nuclei into larger ones. If a nucleus is big like iron, if it's big like uranium, not iron, then it will release energy when it breaks apart. It will not release energy when it fuses if it's big. If it's big, it absorbs energy when it fuses. On the other hand, if the nucleus is small, like hydrogen, that releases energy from fusion. Doesn't release energy from fission. It absorbs energy from fission. So, if big nuclei release energy by breaking apart, and small nuclei release energy by fusing together, would there be a middle ground? Would there be a nucleus that's right there in the middle that does not release energy either way, that does not release energy when it breaks apart or when it fuses together? In fact, there is. It is an extremely important element in astrophysics. Iron. Small nuclei release energy during fusion. Sorry about that. Large nuclei release energy during fission. Fix that mistake. Iron is in the middle. Iron does not release energy at all during nuclear processes. Oh, you can fuse iron together. You can shoot a helium at iron and make nickel. Okay, but you're not going to get any energy out of it. In fact, you're going to absorb energy. It's going to cost you a lot of energy to do that. This happens during supernova explosions. So our sun turns hydrogen into helium. There's a lot of energy released when hydrogen turns into helium, enough energy for the sun. And most stars do that as well. Most stars are turning hydrogen into helium, but eventually the sun's core will run out of hydrogen, and it will, the first thing it will do is it will burn hydrogen in a shell around the core. And then the outer layers of the sun will swell up and it will become a red giant. The outer layers of the sun will engulf the orbit of Mercury, and then Venus, and then Earth. And then eventually the core will get hot enough for helium to turn into carbon. Then the sun will swell back down, and then it'll run out of helium in the core and swell up again. Then it will burn hydrogen into helium in a shell completely surrounding the core. Inside of that is a shell turning helium into carbon, and in the middle will be an inert carbon core. At the very end of its life, there will be a huge burst of nuclear fusion in the core. Some of that carbon will turn to oxygen, and there will be so much radiation and thermal energy generated that the outer layers of the sun will poof out to form a planetary nebula, and the core will be left behind as a white dwarf star, a giant ball of carbon and oxygen that's so dense, 1 teaspoon of white dwarf star would weigh as much as a pickup truck. This is the mass of the sun compacted down to the size of the Earth. Remember, the sun is 100 times the size of Earth by radius, 1,000,000 times by volume. So if you take the whole sun and compact it down 1,000,000 times, that's a white dwarf star. Well, the sun's a low mass star, so its core is never going to get hot enough or dense enough to manufacture anything heavier than oxygen and some carbon. But a high mass star will have even more pressure on its core. Its core will get hotter and denser and hotter and denser. So at the end of its life, it will swell up even more and become a red supergiant. It will engulf the orbit. A high mass star would engulf the orbit of Mercury, then Venus, then Earth, then Mars, maybe Jupiter. And in the meantime, heavier and heavier elements get manufactured inside the core. Carbon captures helium to form oxygen. Oxygen forms neon. Neon forms magnesium. Advanced reactions will make silicone. On up the periodic table, heavier and heavier and heavier and heavier and heavier until iron. See, here's the thing. The red supergiant star is like 10 times the mass of the sun. So what is preventing the outer layers of that star from smashing onto the core? There must be something pushing out. And that something is energy released from nuclear fusion. Radiation pressure, the core is so bright, the light itself pushes outward against the gravity of the outer layers. The light itself helps to hold up the outer layers of the star. Not only that, thermal pressure also. It's really hot, so all those atoms are banging against each other, and that produces an outward pressure that resists the inward push of gravity. But once iron is manufactured, iron doesn't release energy. Iron absorbs it. So once iron is manufactured in the core, within seconds, the core goes dark. There's not enough radiation pressure or thermal pressure to hold up the outer layers of the core. So suddenly you have the outer layers of the core in free fall. The full weight of a red supergiant star, 10 times the mass of the sun, in free fall onto the core. Bam! And when the full weight of a red supergiant star smashes onto the core, some remarkable things happen. First, all of the electrons get smashed into the protons in the core. They get merged with the protons to form neutrons. The core becomes a neutron star. But more than that, when the full weight of a red supergiant star goes into free fall on the core, it hits the core at nearly light speed, which means, bam, it bounces off like a basketball, producing an explosion, a supernova, an exploding star. Iron triggers a supernova. And there's lots of energy to go around. So yes, iron doesn't like to fuse together. It doesn't release energy when it does that, but it'll fuse. It just absorbs energy when it fuses. And hey, a star is exploding. There's plenty of energy to go around. So during a supernova, there's a supernova right there. During a supernova, there's plenty of energy to fuse iron with heavier elements, to make more iron, first off, and to make things like nickel. Iron and nickel are produced in abundance during supernovae. And that's why Earth's core is made of iron and nickel, because there's lots of iron and nickel in the universe that was made by supernovae. Earth's core was made by an exploding star. What you're seeing here is the Crab Nebula. It is the remnant of a supernova that was first cataloged by Chinese astronomers in 1054. It was bright enough to be seen in the daytime. Presumably everyone in the world saw it, but the Chinese were writing things down at this point in history, so thank goodness we have records. So during supernovae, you get a whole lot of heavy elements manufactured, stuff in the middle of the periodic table: sulfur, argon, calcium, iron and nickel, and zinc. Well, humans, for better or for worse, have figured out how to fuse things together and break nuclei apart. This is a 20th century thing. 1896, end of the 19th century. Henri Becquerel discovers radioactivity. According to the story, he put a hunk of uranium in a dark cabinet with some photographic plate, and even though there was no light, the photographic plate was exposed because the uranium was emitting X-rays, because the uranium is radioactive. Humans would not learn to artificially make nuclear reactions until 1933, almost 40 years later. Irene Joliot-Curie bombarded aluminum foil with alpha particles, that's just helium nuclei, and produced phosphorus 30. And then 5 years later, she discovers fission. That is, she bombed uranium with some neutrons, splitting uranium into smaller nuclei. 1938. Gee, what was happening in the world in 1938? Oh, that guy. Oh, you have a guy in power who thinks he's above the law and has absolute authority to do anything he wants to and scapegoats minorities. That can't go wrong. Well, Hitler wasn't too popular among scientists, partly because a lot of his best scientists were Jews, and so he wanted very much to build a nuclear weapon. He understood that the power in nuclear fission was immense, and that at least theoretically it was possible to build a bomb out of this. Fortunately for us, the scientists that he had under him who were most capable of doing that were Jews, and they all left. A lot of them came to the United States. Well, Einstein wrote a letter to President Franklin Roosevelt saying, hey, Hitler, he's a bad guy, right? You don't want Hitler getting a bomb, and he's trying. We don't know if he's going to succeed or not, but he's trying. So I think we should build one first. Einstein would later regret that. According to lore, might be apocryphal, Einstein, when the first nuclear bomb went off, said, I should have been a watchmaker. Nonetheless, he strongly felt, hey, if Hitler's going to have one, we need it first. So the United States built a nuclear bomb. Well, April 30th, 1945, Hitler offs himself. That was a chaotic week for the Nazis. The Nazis surrendered on May 8th, so hey, no more reason to keep making the bomb. Yeah, but we're so close! Oh, July 16th. After the Nazis had already surrendered, the first nuclear weapon was completed and tested in the New Mexico desert. Well, Germany had already surrendered, so you might as well use it, huh? Hiroshima and then Nagasaki, Japan. United States waged nuclear war against Japan, triggering the surrender of Japan. It did its job. Japan surrendered, and the United States continued to build and build and build nuclear weapons. Pretty soon the Soviet Union did the same thing. I have included a link in the a link in the description for a timeline, a video of a timeline of all the nuclear explosions that have ever taken place on Earth. It's worth watching. It's a little trippy. The nuclear weapons that the United States deployed against Japan were both fission bombs, uranium bombs. But in the next decade, 1952, the first fusion bomb, the hydrogen bomb, would be tested. And it is much more powerful even than the fission bomb. Remember, nuclear fusion is how the sun shines. So when you explode a hydrogen bomb, you are recreating the conditions at the core of the sun on the surface of the Earth. So you can imagine why that would be so destructive. You don't want the sun on the Earth. And we keep doing it. The United States has built more than 70,000 nuclear warheads. That's more than all other nations combined. A distant second was the old Soviet Union, which broke apart and now we call Russia, and a few other nations. Russia and the United States together have more than 90% of the nuclear weapons in the world. They have tried over the years to make treaties to limit proliferation with varying success. Some treaties were more successful than others. In 2011, President Obama signed the New START Treaty, Strategic Arms Reduction Treaty, that limited both U.S. and Russia to 1,400 deployed warheads each. That means on the air, in the air, on the ground, on submarines, ready to go. That's deployed. 1,400 is all we have, even though we have lots more in stockpile. In 2019, however, step backwards, the U.S. President Trump withdrew the United States from the Intermediate Range Nuclear Forces Treaty. So it goes back and forth. But really, there's lots of nukes out there and lots of room, not only for nuclear war, but for accidents, which have almost happened several times. Well, that was fun, sort of. So let's end it with some poetry. Say it with me. Small nuclei release energy during nuclear fusion. Large nuclei release energy during nuclear fission. Iron releases energy from neither. It's the most stable on the periodic table. When I say physics, you say rocks. Physics! Did you say it? Yeah, you did. Go do your lecture quiz. Go do it now while it's still fresh.